Hello students, welcome back to our chemistry class. Today we are going to go to 1913. Yes, remember our friend Mr. Henry Moseley and how he found the limitations of Mendeleev's table? He just informed me that he has finished making the periodic table. So let's go and find out how he made order out of chaos. Come on, let's go. We are here again. Oh, hello Henry. Hello ma'am. Hello students. Come on in quick. I have a small job. I'll be right back. Just wait a few minutes. Oh, Mendel is here. Hello children. John's friend Henry has made a huge accomplishment in the field of chemistry. So, this discovery which he has made is going to enable us to discover infinite more things, enlarge our perspective about chemistry. He has gone to receive his award from our president. He'll be back soon. Oh, he has come. Sorry guys, I have not made you wait for too long. I'll explain my discovery first. I found a more fundamental property than atomic mass called atomic number, which is nothing but the number of protons or electrons in our atom of an element. This number is unique for every element, so we can arrange them easily without any confusions. Atomic number is symbolized by the letter Z. So, my law, which is called the modern periodic law, can be stated as follows. Properties of elements or the periodic function of their atomic numbers. So, the elements classified based on atomic numbers are much more efficient because we can predict their properties easily when they are arranged in this way. As we have seen earlier, vertical columns are called groups and horizontal rows are called periods. So my table here has 18 groups and 7 periods. Let's see the properties of elements which are placed in groups and periods. Come on, take group number 17, which is called the halogen family. Likewise, all groups have names. In group 17, let's take the first 3 elements: fluorine, chlorine, bromine. Let's see their electronic configurations. Observe closely. Look, all 3 of them have 7 valence electrons, their valence shell. So, from this, we know that all the elements present in the group will have the same number of valency electrons. We should also notice that the number of shells increases as we go down the group. Now, look at the periods. Let's take the third period. The elements that we are taking are sodium, magnesium and aluminium. Here under configuration, what do they have in similar? Yes, they have the same number of shells. You can also observe that an electron increases in the same shell as we move towards the right. Maximum number of electrons which can be accommodated in the shell is given by the formula 2n square. Look, the first period contains 2 elements. Second period contains 8 elements. Third period contains 8 elements. Fourth period contains 18 elements. Fifth period, 18 elements. Sixth period, 32 elements. And the seventh period contains 32 elements. The reason for this you will learn in your higher classes. The position of an element in a periodic table can tell us about its chemical nature. As we already know, the number of valence shells in an element determines the kind and number of bonds formed by it. So, let's see the trends which are seen in the periodic table. Let's see about the trends in valency. As you know, the valency of an element is determined by the number of valence electrons present in outermost shell of atom. So we know that the number of valence electrons in the valence shell increases as we move from left to right along a period, but it does not change when going down a group. Next, we'll move on to the next trend, that is atomic size. The term atomic size refers to the radius of an atom. The atomic size may be visualized as the distance between the center of the nucleus and the outermost shell of an isolated atom. The atomic radius of hydrogen atom is 37 picometer. 1 picometer is equal to 10 power minus 12 meter. Atomic radii of the element of the second period are given below. Period 2 elements: boron, beryllium, oxygen, nitrogen, lithium, carbon. Atomic radius in pm 88, 111, 66, 74, 152, 77. Arrange them in decreasing order of their atomic radii, or the elements now arranged in the pattern of a period in the periodic table. This is due to an increase in nuclear charge, which tends to pull the electrons closer to the nucleus and reduce the size of the atom. This shows that atomic radii decreases as we move along the period, and it increases when we move down a group. This increases the distance between the outermost electrons and the nucleus, so that the atomic size increases in spite of the increase in nuclear charge. Now, I heard that you guys were really good at metals and non-metals, so I hope that you would have noticed the metals are placed in the left. Yeah, there's sodium, magnesium. There are the non-metals: sulfur, chlorine, oxygen, etc. Now look in the middle. You can see the semi-metals or metalloids like silicon, boron arranged like a slanting zigzag line. The metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, polonium. So there are 7 metalloids in my table. We know metals tend to lose electrons while forming bonds. That is, they are electropositive in nature. Oh, I think I've been lecturing for too long, guys. I was a bit excited, that's all. Look, here is my modern atomic table. I want all of you to draw one of this in your classwork and send me a picture of it. I've asked your teacher to send it to me. Okay guys, I guess this. Bye. Farewell. Okay guys, come on, let's go back. As Henry said, draw a periodic table and send it to me. I will post the picture of the best periodic table in my videos. Until then, bye from your SMLs. Bye.